Next topic is classification of organometallic compounds based on the nature of metal-carbon bonds. Organometallic compounds are of four types: ionic organometallic compounds, sigma-bonded organometallic compounds, pi-bonded organometallic compounds, and multi-centered bonded organometallic compounds. And the first one is ionic organometallic compounds. From the name itself, we can say that such type of organometallic compounds will be ionic in nature. Highly electropositive metals, mainly of group 1 and 2, form ionic organometallic compounds. Cs plus CH3 minus, C6H5 minus Na plus, C6H5 3C minus Na plus. All these are examples of ionic organometallic compounds. Now the second one is sigma bonded organometallic compounds. Compounds in which carbon of the organic moiety is attached to metal of relatively low electropositivity character by a normal 2-electron 2-center bond. Such type of organometallic compounds are called sigma bonded organometallic compounds. Compounds in which carbon of the organic moiety is attached to a metal of relatively low electropositivity character by a normal 2-electron 2-center bond are called sigma bonded organometallic compounds. Here you can see a metal of low electropositive character. These two are examples of sigma bonded organometallic compound. Now the third one is pi bonded organometallic compounds. Pi bonded organometallic compounds are of two types. The first type of pi bonded organometallic compounds contains a normal sigma bond formed by the donation of ligand electrons to the metal, and here sigma bond is formed. The first type of pi bonded organometallic compounds contains a normal sigma bond formed initially by donation of ligand electrons to the metal, and this is followed by back donation of metal electrons to the vacant pi orbital of the ligand, resulting in the formation of a pi bond. So here you can see first a sigma bond is formed by the donation of electrons from ligand to metal. Then in the next step what happens? Back donation of electrons from metal to ligand takes place and to its vacant pi orbital, resulting in the formation of a pi bond. Example, metal carbonyls. In metal carbonyls you can see this type of bonding. So the ability of a ligand to enter into back bonding by accepting electron density from the metal into its vacant pi orbital is called pi acidity. Carbonyl, cyanide ligands have high pi acidity. They can accept electron from metal to its vacant pi orbital. So that is why these ligands are called pi acceptors. Now the second type of pi bonded organometallic compounds are those in which donation of electrons from the ligand to the metal as well as back donation of electrons from metal to ligand are both done by pi orbitals, and such complexes are designated as pi complexes. And here the metal atom is bonded to two or more carbon atoms comprising of pi electron system, and this type of bonding can be seen in ferrocene. Now the next one is multi-centered bonded organometallic compounds, and organometallic compounds which are called electron deficient and occur in polymeric form fall under this category. And examples are what? Examples are LiCH3 4 times, BCH3 twice, N times. All these are examples of multi-centered bonded organometallic compounds. Elements which have the highest tendency to form multi-centered organic compounds are lithium, beryllium, magnesium, boron, and aluminium. So here you can see examples of multi-centered bonded organometallic compound. Next topic is nomenclature of organometallic compounds. We'll see the rules for writing the nomenclature of organometallic compounds, and these are similar to those used for naming the coordination compounds. And the first point is the ligands are usually named in alphabetical order irrespective of the charge on them. And the second one is presence of hydrocarbon ligands in the coordination sphere is indicated by the names of the radicals like methyl, ethyl, phenyl, etc. Although these radicals behave as anions in several cases. So examples you can see here: CH3 4 times Pb is tetramethyl lead, C4H9Li is butyl lithium. The next one is ethyl methyl zinc. Next organometallic compound, the nomenclature is potassium tetraphenyl borate 3. KSBCl5C6H5 is potassium pentachloridophenyl antimonate 5. Now the next point is the hydrides of elements of group 14, 15, 16, 17 and boron can be named by giving an ending ANE to the stem characteristic of element. So for silicon, the name of the hydride is silane. For germanium, it is germane. For tin, it is tannane. pH3, it is phosphine, etc. And organometallic compounds of boron, silicon, tin, etc. May be written as derivatives of their hydride. So C2H5 thrice B is triethylborane. C6H5 thrice is triphenyl phosphine. CH3 thrice is Si twice is hexamethyl disilane. Now the next one is, in the case of unsaturated molecules or groups, the ligand is named with the prefix eta raised to n. If the ligand is an unsaturated molecule or a group, usually we use the prefix eta. So in this particular complex, you can see that these carbon atoms, that is, if you number 1, 2, 3, 4, 5, 6 like that, this 1 to 6 carbon atoms are attached to chromium. 1 to 6 carbon atoms are attached to chromium, and we can name this particular organometallic compound as tricarbonyl 1 to 6 eta 6. Why? Because the hapticity is 6. 6 carbon atoms are attached, and this ligand is cyclooctatetraene. So the name of this complex is tricarbonyl 1 to 6 eta 6 cyclooctatetraene chromium. Now the next one is, this is a salt. The name of this particular complex is potassium trichlorido eta 2 ethene platinate 2. Potassium trichlorido eta 2 ethene platinate 2. Now the next point is, bridging ligands are usually listed in alphabetical order with other ligands, but it is cited before non-bridging ligands, and Greek letter mu is written before the names of bridging ligands. So in the following examples, you can see that here in the first example, you can see that methyl group acts as a bridging ligand here, and the name of this particular complex is dimu-methyl. Why? Because 2-methyl group is present. 2-methyl groups acts as bridging ligand. So the name of that particular complex is dimu-methyl, and 4 terminal methyl groups are present. 4 terminal methyl groups are present. So we can name this particular complex as dimu-methyl tetramethyl dialuminium. 2 aluminium metals metals are present in this particular complex. So the name of this particular complex is diamumethyl tetramethyl dialuminium, or it can also be named as dimumethyl. Why? Because two methyl groups acts as bridging ligand. Bis dimethyl aluminium. Why? Because here you can see that two similar groups are present in this particular complex. Bis dimethyl aluminium. Two dimethyl aluminum group is present in this particular complex. So in another way, we can write the name of this complex as dimumethyl bis dimethyl aluminium. Now this name of this particular complex is dimuphenyl bis dimethyl aluminium, or dimuphenyl tetramethyl aluminium.